Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we are looking at nucleophilic aromatic substitution reactions on benzene rings. And before we move into examining such reactivity, we need to understand why aromatics typically do not undergo nucleophilic substitution reactions. We're going to begin by comparing aryl halides to what we learned about regarding alkyl halides. If you remember, alkyl halides were known or observed to readily undergo nucleophilic substitution reactions. These were typically caused by the polarity of the carbon-halogen bond. So if we had a nucleophile that possessed a negative charge, it could react nucleophilically, either SN1 or SN2, with the alkyl halide. The nucleophile was attracted by the delta plus on the carbon, and you produced a carbon nucleophile bond, and the leaving group halide was observed as an anion. Now, aryl halides undergo nucleophilic substitution reactions better put in nucleophilic. Nucleophilic substitution. I'll just use a superscript N for substitution. Reactions undergo nucleophilic substitution reactions with great difficulty. Why? Well, the explanation for this has four main points. The first point is that the bond from the halogen to an sp squared carbon is stronger than from a halogen to an sp cubed. So 1. The halogen bond to the sp squared carbon is stronger. Stronger than the halogen bond to the sp cubed carbon. So, the halogen bond to sp squared carbon is stronger than the halogen bond to the sp cubed carbon. This is because of greater S character. Sp squared has, the sp squared carbon has greater S character. And what do you know about s orbitals? They are smaller, less diffuse than p's, which means the sp squared is shorter. Shorter bonds are typically stronger. sp squared overlapping with the halogen orbital will make a shorter bond, stronger bond than 2sp cubed. All right. Point 2. We've already seen this in the resonance structures we've drawn for electrophilic aromatic substitution. Resonance stabilization. Resonance stabilization in your aromatic halides. Let's call them Aryl halides. Strengthens the carbon halogen bond. CX bond, X being halogen. And you saw us draw resonance structures, something like this, where we had the aromatic ring, and we had a halogen, and the halogen can dump in a lone pair, and we use this to explain orthoparadirection, why halogens were orthoparadirectors. Yeah. Okay. This type of resonance stabilization, the formation of some pi interaction to the halogen, strengthens the bond slightly. What is our third rule? Well, our third rule, rule number 3, is the one we use most often. Benzene rings, aromatic rings. They're electron rich. Due to pi electrons. Due to pi electrons. Electron-rich nucleophiles shouldn't attack the ring due to electron-electron repulsion. So, electron rings, electron-rich nucleophiles electron-rich nucleophiles will be repelled. All right. Lastly, you're unlikely to undergo SN1 types of reactions generating carbocations because phenylcarbocations are less stable than even primary carbocations. Now, notice this is not, the phenylcarbocation is not the resonance stabilized benzenonium ion from electrophilic aromatic substitution. I'll draw the two. In an electrophilic aromatic substitution, the ring was attacked by an electrophile, and you produced something like this. You had the H, your electrophile added by grabbing the electrons, and that put a plus here. Because there is an H off the carbon with the plus, there's an empty 2p orbital. That empty 2p orbital can delocalize the pi electrons, so there were resonance structures, and this was called a resonance stabilized benzenonium ion. So you had something like this. Now, this resonance stabilized benzenonium ion is not a phenylcarbocation. A phenylcarbocation is one in which a halide leaves a Cl-. All double bonds of the ring are still intact. And you say, well, isn't it very stable then because it retains its aromaticity? And the answer is no, because once you lose chloride, you have a plus. Instead of the plus being in a 2p orbital that can side-to-side delocalize, this plus is in the sp² orbital, an empty orbital. It can't delocalize into the ring because the p orbital is already used making the pi bond. So this is not what that is. If you were to compare the two by looking at an edge-on view, if you had your H and E here, your 2p would be the plus here, because it would have an H. Your empty orbital this orbital would be my positive. It would be empty. All the other guys would have electrons, and so you can side-to-side delocalize into that orbital. Okay, so the electrons here, 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 and here can help stabilize that positive by delocalization. If you look at the same edge-on view, you draw your two p's. The empty orbital is not one of the two p's. Each of these orbitals have an electron. The empty orbital is perpendicular. That has the plus. Whereas these guys can side-to-side overlap and interact. The empty orbital is not available, and so it's totally isolated on this carbon. So phenylcarbocation is extremely unstable. Why? Why would they be less stable than the primary carbocations of an alkyl halide? Well, alkyl halides are sp³. The orbital reaches out further into space. An sp² orbital is held closer to the nucleus. And that empty orbital, because it's closer to the nucleus, is more electronegative, wants more electron density. Therefore, it's less likely to prefer the positive charge. So phenylcarbocations are even less stable. Well, given this, given these four reasons that aromatic rings don't undergo nucleophilic substitution, we must begin to overcome some of these reasons if we want to initiate nucleophilic aromatic substitution. Now, there are two approaches that can be taken to initiate nucleophilic aromatic substitution. One is to overcome point 3, and that is remove the problem of the electron-rich pi cloud by putting on electron-withdrawing groups. If we place electron-withdrawing groups like Nr3+ or cyanides or nitro groups, electron density would be withdrawn from the ring, and as you put more and more delta plus on the ring, you will increase the odds that a nucleophile can attack. The other alternative is to overpower the repulsion in the ring by hitting it with extremely powerful nucleophiles under very harsh conditions. We're going to examine both conditions and both situations and take a look at how the reaction proceeds. Let's begin first with a standard chlorobenzene. Now this chlorobenzene has no other electron withdrawing groups on the ring, so the pi cloud is fairly electron rich and should repel most nucleophiles. And this is really well exemplified if you use a fairly weak nucleophile. And when I say weak, this in alkyl halides was considered a strong nucleophile. But there are stronger. Okay, so as compared to some of the nucleophiles we're going to look at, this is weaker. But in our scale in SN1 and SN2, this certainly was ranked as a strong nucleophile. If I take a 10% aqueous solution of sodium hydroxide, okay, so I'm going to use sodium hydroxide 10%, so it's in water, I will get no reaction unless I go to 350 degrees Celsius and 300 atmospheres pressure. This is what I mean by overpowering the repulsive nature of the pi cloud of the electrons. If you take an average nucleophile, a moderately strong one like hydroxide, you still have to really heat the solution up, really pressure it up to overcome that pi cloud and initiate nucleophilic substitution. If you do that, you will displace the chloride and you will produce phenol. Now this can also be initiated, okay, through a different mechanism using a catalyst. Now we're not going to look at the mechanism of the catalytic procedure, but if I use sodium hydroxide with copper, it would go by a completely different mechanism, but we can lower the harshness of the conditions. We can bring it down to 200 degrees C and 250 atmospheres pressure. So a catalytic process by an alternative mechanism, and let's just indicate that this does not go by the same mechanism. It's catalytic. The copper causes it to follow a different pathway. You can produce phenol. Now, what happens if I put electron withdrawing groups on? What happens, for example, if I go to the extreme case? Well, let's just add one NO2 group on. Start with parachloronitrobenzene. Well, if I hit this with hydroxide, sodium hydroxide at 160 degrees C, I believe it's 160 degrees C. I don't need the high pressure anymore, and I can cause nucleophilic substitution to occur. Clearly, the electron withdrawing group, NO2, which we know, if you go back to electrophilic aromatic substitution, withdraws electrons by electronegativity, electronegative nitrogen to electronegative oxygens, and by resonance. Clearly makes the ring more susceptible to nucleophilic attack, and we can produce paranitrophenol. If you go to a heavily electron withdrawn ring by putting on lots of nitro groups, you can make this molecule react with warm water. Just warm water. A little bit of heat, a little water, and you'll get to 2,4,6-trinitrophenol. Okay. Now, what's really interesting is if we look carefully at these two reactions, specifically, I'm going to rub out this catalytic one. You should know the catalytic one and the conditions for it. But it does its own thing. It goes through a unique mechanism involving the copper catalyst. But essentially, we have two different pathways by which we can make or carry out a nucleophilic aromatic substitution. We've got pathway number 1, where we don't have electron withdrawing groups, and we have pathway number 2. Well, how do we know there are two different pathways? Well, this becomes obvious if we use something like perchlorotoluene instead of our chlorobenzene. And if we react this guy with sodium hydroxide, heat, pressure, notice this is like perchlorobenzene in that there's no electron withdrawing groups. We have only an electron donating methyl group. We actually get two products. We get the expected paramethylphenol, but we also get metamethylphenol. Metamethylphenol. We get these two products. If we compare this to a situation when we have electron withdrawing groups on the ring, you get only substitution where the chloro was. You get only this guy and only him. The only rationalization for the difference has to be that there must be some difference in the reaction mechanism. So we need to look at the reaction mechanism for the nucleophilic substitution itself. What we're going to do is we're going to begin by looking at the substitution when there's electron withdrawing groups on. So let's look at this case first. Notice that I can use several possible nucleophiles. I can use a very powerful nucleophile. We'll look at some reactions with different nucleophiles. The previous slide used hydroxide, but I can take ammonia, deprotonate it, and make sodium amide. If I use NH2 minus, it is a very powerful base and nucleophile, and it can be used without the heat and pressure, or at least not as extreme heat. Now the reaction mechanism for both of the groups, whether you have electron withdrawing or electron donating, is nucleophilic aromatic substitution. But the one we're going to look at is one that is referred to as addition elimination. Addition elimination. Now the addition elimination mechanism actually occurs when you have electron withdrawing groups off the ring. Step 1 is the addition. And it's actually the addition of the nucleophile. And if I take, for example, say I've got NO2 in the para, let's use the parachloronitrobenzene. And I react it with a nucleophile. Let's use amide, NH2 minus. It's a powerful nucleophile, has 2 lone pairs on it, and it's in liquid ammonia. I will get essentially he'll dump in his 2 electrons there, and that'll push those 2 electrons out, and I'll get a negative charge in this position. And I get a resonance stabilized carbanion, aromatic carbanion. I can, for example, bring that lone pair in to this position and move my electrons here, just so you can see what the nitro looks like. Let's actually draw the Lewis structure end of the nitro. That is, you have an O minus and you have a double bond O, and nitrogen is positively charged. We get a lone pair here. We have our Cl, our NH2, thusly. Now I can continue moving that lone pair around the ring. Now that you've seen what the NO2 looks like, I'll just go back to writing it as O2N or NO2. Two electrons move here. And how did that form? My 2 electrons moved here, and the pi electrons moved out here. Okay. Now, just to show you, you can get the same thing whether you have the meta-nitro group. If I had started, for example, with meta-nitrochlorobenzene, I would have gotten, if I started with that, I would have gotten the exact same resonance contributors, except I would have an NO2 in the meta position. Now here we draw them. And there we go. Now, what you see here is the same product made by amide attack, nucleophilic amide attack, that is allowed because of the electron withdrawing capability of the nitro group. The NH2 adds nucleophilically. The carbanion that forms has no pi bonds to the carbon bearing the lone pair, and so the lone pair can be in the 2p orbital and can delocalize by resonance around the ring. I have 3 resonance structures for when the nitro is para and 3 resonance structures for when the nitro is meta. Why would the para carbanion, that is when the nitro group is para, okay, that is this one, why is it more stable? Well, it turns out that this structure right here has some special stabilizing factors. This resonance contributor is especially stable because the carbanion, the negative charge, is next door to a positive. The positive charge helps stabilize the negative. Because nitrogen is so electronegative, it helps stabilize the negative charge, making this resonance structure more stable than any of the resonance structures in the meta case. But it's not just that. I could dump that lone pair here and move these pi electrons out and generate a 4th resonance contributor. And I'll draw that here. And so my 4th resonance contributor looks like this. More delocalization of the negative charge, more resonance contributors means more stable. This carbanion intermediate is more stable, low energy of activation for its transition state, it forms more readily. And so when the nitro's para, and by the way this also holds true for when it's ortho, it takes a little less energy to get the nucleophilic substitution going than when the nitro is meta. So step 1, addition of the nucleophile yields this resonance stabilized carbanion. The electron withdrawing group neutralizes and helps delocalize the negative charge of the anion. Stability is increased and the energy of activation is lowered. Therefore, the reactivity towards the nucleophilic substitution is increased. This is the slow step that we're looking at. NO2 withdraws electrons from all positions by electron withdrawing effects, and when ortho or para, you get an additional resonance structure for the carbanion. Well, what's step 2? Well, obviously step 2, if we just redraw the resonance stabilized carbanion, step 2 is the reformation of the aromatic ring, or elimination of the leaving group. Hence the term addition elimination. What are we eliminating? The good leaving group Cl-. Nucleophile comes in and attacks. We have the resonance stabilized carbanion as our intermediate. So we have Cl, we have NH2. Our nitro is para. And we've got this negative charge and lone pair. Very fast step will be the restoration of aromaticity. Yes, you can disrupt it with a powerful nucleophile, but that disruption is temporary and chloride will leave. And what we will end up with, of course, is the restored aromatic ring with the NH2 on it, paranitроaniline in this case. And we'll have the leaving group Cl-. So it's called addition elimination because nucleophilic attack, the nucleophile adds first, and then we eliminate the chloride in a second step that's quite fast. Well, what happens in the case when we don't have an electron withdrawing group on the ring? Well, it turns out the ring is just far too rich. Just far too rich. Suppose I have a methyl. To allow for nucleophilic attack. The pi cloud of electrons repels even strong nucleophiles like NH2-. So if we react with NH2-, and we have liquid ammonia, what happens? Well, what happens is NH2- is not just a nucleophile, it's also a very powerful base. And he can go for the proton. If he grabs the proton, I would go through a very, very short-lived carbanion intermediate if he grabbed the proton. And if you look carefully at this carbanion that would form, it's not like the carbanion we formed in step 1 of addition and elimination. It would look like this. Because there's still the double bond here, that pi bond is intact. That means the 2p orbitals used in the pi bond. That means the lone pair is not in the 2p orbital. It's perpendicular. It's an sp² orbital. It means it's isolated on this carbon. There's no resonance stabilization of this carbanion. Extremely unstable. NH2- can pull it off, but this is not going to last very long. And the chloride, being a good leaving group, will leave really quickly, taking the Cl-. And so what happens is you get an intermediate that looks like this. What is that? We get an intermediate that looks like it is a methyl benzyne. The benzyne intermediate. Now this is huge because this would represent step one of our proposed mechanism for when there's no electron withdrawing group. And, you know, when we think of triple bonds, we think of sp hybridization, overlap of 2p orbitals side to side, making 2 pi bonds. And what shape is it when you have sp hybridization? Bond angles of 180 degrees. Well, with a 6-membered ring, you cannot get bond angles of 180 degrees. So what we have here, step one, okay, step one is elimination. Elimination of a proton and a chloride. So whereas addition occurred first when there's electron withdrawing groups on it, when there's electron donating, we get elimination. The NH2X is a base, grabs a proton, we kick out HCl, and we get this thing called benzyne. But it's not your normal sp hybridized carbons. The ring is 6-membered. It's flat. Bond angle has to be 120. This guy's staying sp squared. How can you have a triple bond in an sp squared situation? Well, if we draw an edge-on view, you put in your 2p orbitals. Now I'm going to move if you don't mind, I'm going to rotate the ring a little so you can see it better. You get a pi bond here, a pi bond here, pi bond here. And I'm going to make, here's an sp squared orbital that's empty, and I'm going to make this orbital sp squared. Let's draw it in a different place. Maybe I can draw it here. There. Okay, let's do that. Okay, so fix this up. So here's one 2p orbital, another, and these two orbitals interact side to side, but they're sp squared. If you looked at it, rather than a 2p, these are orientated away from each other, and so their side-to-side overlap is less efficient. So one of these pi bonds in the benzyne is a pi sp squared orbital. That would be extremely reactive because the overlap is not as efficient as when you have side-to-side 2p's. Straight up and down, side-to-side 2p's will overlap more efficiently than when you have two orbitals that are pointed away from each other. The side-to-side is less efficient. So the benzyne is extremely reactive because of the sp squared. But what's really interesting is in the case of benzyne, when it's attacked by a nucleophile, in the second step, when there's the addition, which side of the benzyne do you attack? Do you attack here or do you attack here? And the point is, once you've made the benzyne fragment, attack at either sp squared orbital is equally probable. And so this leads to our product distribution. Remember, I said, if you take perchlorotoluene and you react it, with hydroxide, you got two products. Well, if you take perchlorotoluene and you react it with sodium amide, the same thing happens. You take amide, NH2, which by the way has two lone pairs, in liquid ammonia. You not only get paratoluidine, but you also get metatoluidine. Whoa. And you can begin to see how that becomes feasible, how Benzyne would allow this to occur. Because if we had this methyl substituted Benzyne, and it's going to undergo step 2 where the nucleophile is going to attack the pi sp squared, there's two positions it could attack, here or here. If you attack here, you get the para. If you attack here, you get the meta. So this Benzyne postulate works out really well in explaining the product distribution. Well, before we look at more evidence for the formation of Benzyne, why didn't we take a look at the second step? So in the first step, we get the NH2 minus attacking as a base, and we get elimination of HCl. What is step 2? Well, step 2 is addition, obviously. Addition of the nucleophile. Benzyne being so reactive, the sp squared orbital overlapping so poorly and becoming so reactive, we get nucleophilic attack to make a carbanion. We get the addition. So we get our methyl substituted Benzyne gets attacked. And it can get attacked in one of two positions. So you can either have the NH2 minus add to the meta position, or it can add to the para. When it does, the pi electrons will move out and you'll get a carbanion. So let's take a look at both possibilities. If I add para, then the pi electrons will move over here. I'll get this negative charge. If I add meta, I'll get this NH2, it adds to this position, and I'll get the negative charge here. Now look at both these carbanions, and once again you see the carbon with the lone pair that has a negative charge has a pi bond. That means the 2p orbitals are being used for that pi bond. That means the lone pair is not in the 2p orbital and hence can't delocalize around the ring. This carbanion is not resonance stabilized. That lone pair negative charge is stuck on that carbon. So this guy's extremely basic. And NH2 minus is in a solvent called liquid ammonia. So these guys can react with the liquid ammonia, grab a proton off the liquid ammonia, which will turn to NH2 minus. And you will get the proton on the aromatic ring. And you'll end up with paratoluidine, and of course the metatoluidine. So there you have it. Let's fix that up a little bit. So this comes off as NH2, two lone pairs, minus. Okay. So the two steps in this mechanism are elimination and addition. So when we have electron withdrawing groups on the aromatic ring, we undergo addition elimination. We add the nucleophile where the chlorides attached, get a resonance stabilized carbanion, and then we eliminate to restore aromaticity. When we have no electron withdrawing groups, we get elimination addition. Nucleophile can't attack, so it acts like a base, pulls out the proton, you lose HCl, and you get benzyne. When benzynes attack nucleophilically because it's so reactive, you get a carbanion that's not resonance stabilized. It quickly grabs a proton. And you end up with substitution at both positions of the benzyne. Now, if it was just chlorobenzene, you would not see this. It's because I put the methyl group on the ring that I actually see the para-meta substitution. If I just use benzyne, it wouldn't matter which side I attacked. I would get just aniline as the product. Okay. Is there any further evidence that this benzyne formation, this mechanism of elimination addition, is being followed? Well, the slow step, of course, is making this very reactive benzyne molecule. And the first step requires removal of hydrogen, the elimination step. So if we prevented this first step from occurring, we should get no reaction. We should be able to see no reaction occurring. And we can do that. What we can do is we can make a molecule like this, where instead of chlorobenzene, we have substituted both alkyl positions, one with a CH3 or one with a methoxy. So if you like, I have 2-chloro-3-methyl anisole, and we hit this guy with the NH2- in liquid ammonia. And if you hit this guy with this powerful base, he can't follow this mechanism because there's no protons to pull off and eliminate HCl. You must pull off an H next door to the Cl to lose the HCl. Okay? You can't. Transfer the electrons if you don't lose the H. And because there's nothing to pull off, there's no reaction. So this is some evidence that hydrogen abstraction is required in the first step, the hydrogen abstraction we saw necessary to form benzyne. One further argument you could make is that, or one further question you could raise, all right, maybe you've established benzyne by the formation of the two products here, in this case, but what about benzene? Maybe when you have just chlorobenzene, you actually go a different mechanism because you only get one product, aniline. Well, we can go a further step, and we can look at chlorobenzene and use isotopically labeled chlorobenzene, where this carbon position right here has been enriched in either carbon-13 or carbon-14. Carbon-13 has a nuclear spin, is capable of being observed by nucleomagnetic resonance spectroscopy. Carbon-14 is radioactive. In both cases, you can track what is going on if we substitute for this molecule with sodium amide. So we substitute the isotopically labeled chlorobenzene with sodium amide and liquid ammonia. Whereas there was no reference to see whether you were actually getting two anilines, now there is. And indeed, you substitute for the chloro, and you get NH2 in this position. Right on. But you also get the NH2 meta. Oops. You also get the NH2 next door, not meta, ortho to the labeled position. And this is exactly what we would predict based on the benzyne intermediate. Our last suggestion that I have to give you is that whenever you work with this type of mechanism where there's no electron withdrawing group on the chlorobenzene, you don't have electron withdrawing groups, you have just chlorobenzene or electron donating group. Always draw the benzyne and look at it. Why? Because sometimes it's a bit tricky in figuring out what actually forms. Suppose you tried to do this reaction with meta chloromethylbenzene. Same reagents, I'm not going to write them down again. NH2 minus, oh let's write them down. NH2 minus liquid ammonia. And if you're not going to draw the product or the intermediate benzyne and figure it out, some people will just forget and treat it just like that methyl was a nitro, and they'll just substitute the chloro. And they'll give you this as the product. And a few others might remember that you could get the benzyne forming, and so, oops, that should be a 2. And they might even go this far and say, okay, you get both that. There, now I've hit my benzyne. I've covered everything. I'm done. And if you do this, you're going to get the answer wrong. And the only reason you get it wrong is you didn't take the time to draw the benzyne intermediate. What do I mean? Well, draw the benzyne. Lose the chloro. There's an H here. I can have amide pull off this H. If that H gets removed, the benzyne I'm going to make is this guy. Right there. But there's also an H here which the base can pull off. And if the base pulls off that H, I will also get that benzyne. Now, if you take the time to draw this, and you know you can get attack here and here, well, those are the two products I've drawn. But I also can get attack here and here. You see there's a third product. Not only can you get meta and ortho toluidine, but you also can produce the paratoluidine. There you go. And only by drawing both benzynes that form will you be able to see this. One last piece of evidence for the existence of benzyne has to do with the reactivity of the pi sp squared bond that forms. What we're going to do here is attempt to form benzyne by reaction with magnesium metal. We know that magnesium will insert in a bromine bond on an aromatic ring to make Grignard reagent, phenylmagnesium bromide. If the magnesium would combine with the fluoride and make a magnesium bromofluorous salt, it is possible that you would produce benzyne. Now this benzyne is extremely reactive. It's not going to be isolable. But we would expect the reactivity of the pi sp squared and sp squared to be so strong, so reactive, that if it did react, it would act very much like an alkene. And we could use it as a dienophile to attack a diene. And if we did this reaction in the presence of a diene, such as anthracene, which would look like this. Right here, this pi group could attack here and here, where this is our diene. This would retain aromaticity on the other rings. And indeed, does happen. And you produce the molecule Triptycene in 28% yield. And the only way this could form is if this guy added on top of that ring. Let's use some different colors to show this reaction a little more clearly. I'm going to use black to draw my benzyne. So I'm going to redraw the benzyne in black. I'm going to leave the dye in blue, but where the Diels-Alder reaction occurs, the bonds that join up, I'll draw them in red. So what happens is we get bonds here and here, and we form our ring. And this is the tryptosine molecule that adds across the pi bond. It's a Diels-Alder reaction, and the dienophile of the benzyne adds. The fact that you could get a Diels-Alder reaction on the product, this suggests the presence of the benzyne molecule. Lastly, I want to refer to one last very good leaving group that we can get, and that is the sulfonic acid group found in benzenesulfonic acid. We can take benzenesulfonic acid and substitute for it under a variety of conditions. We can, for example, treat benzenesulfonic acid with acid and water. Now this reaction is rather strange in that we get benzene plus H2SO4. And you might recall that, hey, we took benzene with H2SO4 in pure concentrated form, fuming sulfuric acid, made Benzenesulfonic acid. This suggests that there's an equilibrium here where, depending on the presence of the electrophile, we can reversibly remove the SO3 group. Acid in water allows the SO3 to come out as H2SO4. Pure H2SO4 fuming with SO3 drives it back to the left. Or so it would appear. We can hit Benzenesulfonic acid with sodium hydroxide fusion. Fusion meaning that we melt the sodium hydroxide pellets, we heat them up, we make them undergo melting. It's really molten sodium hydroxide to which you add the benzenesulfonic acid. This will produce phenoxide, anion, you add acid, H plus, to protonate it, and we can make phenol this way. And the last point is the SO3H group is such a good leaving group that is, you have it on an activated ring. Like parahydroxy benzenesulfonic acid. A couple points. Br2 does electrophilic aromatic substitution in the presence of FeBr3. We've established that. If the ring's very activated, you don't need the FeBr3. And you can get substitution, electrophilic aromatic substitution. Now, if you use excess Br2, you would expect to get substitution on the ortho positions because there's no H to pull off. The HSO3 is occupying the para. But the HSO3 group is such a good leaving group that you also kick it out. And so if you use excess bromine, you will put not only bromines ortho, but you will kick out the HSO3 as H2SO4, and you will make the tribromo adduct. Well, there you have it. That's nucleophilic aromatic substitution. We've looked at addition-elimination and elimination-addition mechanisms. This is Dr. Brian Lloyd signing off from his Scribblecast.